But basically the idea is you go left to right, and then thanks to all kindness unscared. If your Y value is going up, and one is going down. You catch your breath and the noise will present you the technically are closed intervals. I'm most likely going to use open intervals. Not necessarily something that wouldn't like trick you on a test or anything like that. But if we use open intervals, that when we have discontinuity, you'll see that that'll make it easier if we just use open intervals at all times. That a little later. I see that particular function that's right here. Let's go from increase to decrease. You've got a horizontal line right there. Derivative of 0. Got the critical number. And down here, we have another critical number. Got the relative maximum on top and relative minimum on the end. Now I did this on a closed interval. Most of the time when we're using open intervals for variable type functions that are strict, we'll use that in the thing as this is. But I just did this example of closed interval. So we would say that F is increasing in the direction of B, and increasing again from C to D, decreasing from D to C. Now notice something in the interval, it's the first interval increase right here, from A to A to B. Now I can do a couple of random tangent lines. They're all separate more, but you get the idea. Notice that in that entire interval from A to B, you put a tangent line there, and at any point, you're going to have a positive slope. Therefore, you can say that if you are in an interval that is increasing, and you really on all the B, the derivative of any value in that interval is positive. Slope is positive. Now we come down the middle. Next one is C1C. There are a couple of tangent lines. The tangent slope value is negative. Therefore, the derivative would be negative in that interval from B to C. Then as you increase, all these tangent slopes here again would be positive. So we're just about to tie that idea in positive and negative derivatives in with increasing and decreasing. Now look at this one, this graph. Now this B is a critical number. It's actually a relative minimum, but the derivative doesn't exist at B. But we've seen that in the section section on extreme on an interval. There's two ways you can get a critical number. The derivative cannot, it's possible the derivative does not exist, yet the function itself exists. That's what this is saying right here. That's the second part. That's what I'm drawing right over here, as I'm indicating this is one way you get critical numbers, and this is another way you get critical numbers. So that's the two definitions of the critical numbers are used separately in each of these two problems. So we have decreasing from A to B, and then increasing from B to C. So as you can tell now that we look at an interval, and if we know that all the slopes in the interval are negative, we have a decreasing function. If the derivative is positive in the interval, you have increasing function. And that definition is coming right up. Here it is. Positive for all x in your interval A to B, then f is increasing. If the derivative is negative, it's it's decreasing, and the derivative just happened to be 0 for that interval, you have a constant function, meaning you have a horizontal line for that segment. I don't think we're going to see that come up too much. At least I'm not going to bring it up that much unless it was a picture. You're not going to have a graph. You're not going to have an equation that generates a graph like this unless it was a piecewise function. It would have to be such a thing where it generated pieces to make it look like that. There's no f of x in one piece that'll go up, curve, go flat, and then angle down like that. Well, we would say, okay, increasing from A to B, and then it's constant from B to C, and then decreasing from C to D. Like I said, you may have to read that constant function off of a graph if you won't have it in an equation. Now, let's look at the process that we want to do to find our intervals of increasing and decreasing. Notice I don't even put constant in the title because I'm not going to worry about that unless it's graph. So increasing and decreasing it is. There's two things that affect the flow of the graph and change from increasing to decreasing by those are the critical numbers and discontinuity. So we have to find for any function all critical numbers and discontinuity and then our graph on hand. But we're looking for any of the combinations of critical numbers. There will be these values to separate the number line, the real number line, different intervals. Most of the time we'll be working with real number line with the exception of trig functions, we'll be just using 0 to 2 pi for those. This isn't like, finding, absolute mins and maxes and stuff where you be given a closed interval. So we're just going to treat this as an entire open interval from negative infinity to infinity. Then, once you have your interval set up, all you have to do is pick a test value in each interval. As long as you have the right points of separation, all you got to do is pick one point in that interval, and if the derivative is positive, it'll be positive for all values in that interval. If it's negative, it will be negative for all values in that interval. And then using theorem 3.5, determine increasing and decreasing. A positive interval will be increasing, and a negative interval will be decreasing. All right, here's a nice, easy polynomial to start off with. Certainly no discontinuity here, but critical numbers are certainly fair game. So we have h of x equals 12x minus x cubed. Derivative sine of x equals 12 minus 3x squared. Set this equals 0. We'll know with x squared equals 4. When I mentioned this in other videos, I'm probably tired of hearing it, but I'm saying it every time. It's important. The x squared equals 4 has two solutions, plus and minus 2. Now we have certain applications that we dealt with, like Wolf's theorem and value theorem, where you might toss an answer out if it's not in the interval. But we're dealing with the real number line, so everything counts here. So anything tossed out. But if you don't get the most plus or minus 2, well, you really mess this up. Alright, let's create a little sign chart here, so we're going to have a book of this, and put this in intervals. I'm on a handwritten test, I'm not too sticky about use this type of notation, so use interval notation, that notation is very alright. Yeah, I'm going to go ahead and use open intervals here. Just like I said earlier, the definition of a closed interval, I'm going to use open because infinity is open. Yeah, but the continuity is open, so you can leave everything open, let's not worry about it. But yeah, but just for the sake of argument, wherever you have negative and positive, that's alright. No way to very much. positive 2, basically put the real number on it. So I'll do 6 test values. Something less than that, because I don't know why that's 5. So anyway, you plug in negative 5. The main thing here is not then I picked something between negative 2 and 2, so I chose 1. Don't know why. I should have chosen 0. That's what I usually do when I pick them, but oh well. Anytime I can use 0, I generally put 0 in there, because 0 would be so easy to look at this and realize it's going to be 12. It's going to be positive. So either way, it didn't matter. 0 would have been positive. 1 is positive. So that's the whole idea of picking any number you want in the interval. And something larger than 2, I chose 3, plugged that in there, and got negative. So it goes negative, positive, negative. That means decreasing, increasing, decreasing. Here's what a graph of it looks like. Decrease, increase, decrease. And there we go. That's it. There's the same idea, a different problem. Increasing, decreasing. And y equals x plus 9 over x, which I just wrote this way for derivative purposes. Right off the bat, you see we've got discontinuity. Discontinuity of x equals 0. Discontinuity must go on the sign chart. No matter what. No matter if you have no critical values, which could happen. No critical values, you still got to put that 0 on. Alright, so I take the derivative, 1 minus 9x to the minus 2, 1 minus 9 over x squared, set 9 over x squared equal 1, and here we go, x squared equals 9, plus and minus 3, so we have 3 values that go on the sign chart, plus and minus 3 are critical numbers, 0 is a discontinuity. So I'm going from negative infinity to negative 3. Negative 3 is 0. 0 to 3. And then 3 to infinity. Now, in a little while, I'll talk about why I have this dash line there. Don't worry about it for now. But I will explain that at some point. So I get a start here. Keep in mind, we are plugging in the derivative. Don't believe this fact that we're going to absolute minutes and maxes, things like that. You were plugging these into the original function because you wanted to know the y value. That's not what we're looking for here. We're looking for what the sign of the derivative is. Right over there, the sign of f prime. So you do want to plug these into the derivative. You've got to pay attention to what you're plugging into and why. Anyway, I just did like this. I typed in this derivative, as you can't see it. So obviously, you can verify and let me know if I got it wrong or not. Kind of like y prime in there, so I put less than negative 3, I put negative 4. Between negative 3 and 0 and negative 2. So 1. Greater than 3, I put 5. I want to keep the line small so that they could have. Yeah, I said you would have to use a decimal set. 0.5, something like that. So that could happen. You won't always be able to use an integer, most of the time. Either in green, the negative 4, negative 2, 1, and 5, here they are in the box. On the y prime, all I care about is the plus or minus on that number. So, plus, and then back-to-back minuses right here, minus, and point to 4 or positive. The graph goes increase, decrease, decrease, increase. Let's watch this. So it goes increase here, decrease, and starting from the other side of 0, it's one left side here. Decrease again, it's right there, and then increase. So I like it. I like what we did there. Oh, a trick one. Always fun and challenging. Not always the most popular one. So cosine squared. I like this. It's a good practice. Same rule practice.
Sitting by the road, the bastard's gone away.
Cosine squared. Cosine. A lot quicker to figure out the threshold. This trick function won't have any good time notice, so we're not, well, I say well. I usually don't use anything like that. Anyway, as long as cosine sine, we can say later.
Just the combination will have changed. Someday they'll catch me to a chain and attach me.
So basically, here's what's happening. And bring the T down. There's a lot of people with this that
I'll stay out of jail for paying my bail. And after a word for other people saying you've done me wrong, it's the same old song.
And then that changes this exponent to 1. And then you take the derivative of cosine. Think of it this way. Think of it as cosine is the derivative of squared. Just like this. Y squared. Y prime equals 2 u. You can either say u prime or du, same thing, but this is right. 2u u prime. Chain rule. And then du, the derivative of cosine would be negative sine. Then the derivative of negative cosine would be positive sine. Okay, so we're going to set this equal to 0. So you're looking for factoring stuff here. They share a common sign factor. So we factor out a sine, and that will leave me a negative 2 cosine x plus 1. Obviously you got a 1 there, so that distributes out to be correct. So now we can set each of those factors equal to 0. See, we're in the open interval 0 to 2 pi.
In search of another to share in his life. No.
This is the one time, the trick problem won't start at negative infinity and go to positive infinity.
They got no horns and they got no
So sine of x equals 0. Now it equals 0 is 0 pi to 5. So notice I have the open interval 0 to 5. So in the open interval, not including those endpoints. We're talking about this down here pi. Now you take this one, negative 2 cosine x plus 1 equals 0. That gives you cosine of x equals 1/2. So in the unit circle, between 0 and 2 pi, that gives me 2 values. Pi over 3, pi over 3.
The beast that can talk.
So we have 3 critical numbers that go on our chart, and then therefore we will have 4 sections. 0 pi over 3, pi over 3 pi, pi, pi over 3, and pi over 3 pi. Now, You don't know what the break-in mode. I'm trying to find something different more traditional values of the card, you know, like miles, 5 or 4, 5 or 6. But I'm using radius measures that are accurate. Because, pi over 3 would be 3.4 divided by 3. It's a little more than 1 radian. So I put 0.5 radians. Same thing here. A little over 1, a little over 3. So I put 2 radians. But if you're more comfortable with the value on the circle, I just do it real quick. I knew that 4 would fit in this one. 6 would fit in that one. 5, 6, 1, 2, 8. So I type them in up here.
Am I wrong to believe in the city of gold? Lies in the deep distance.
Yeah, I grabbed the bottom one for the derivative. I didn't graph the derivative, you see from up here. See, I have that label Y2, the Y1. That's the one I want to plug the values in. I want to graph Y1, but I want to get the values of the derivative. Man, that looks pretty good, so I scaled this by pi over 3. So it's going down, pi over 3, decrease, increase, pi, decrease, pi over 3, increase, pi. That's beautiful. Alright, let's talk about other side with a topic we talked about before. Relative minimum, relative maximum. I put the word local in there. For some books call them local minimum or local maximum. School maintains a textbook that uses that phrasing instead, so I wanted to put both in there. But as long as with the Larson book, they definitely use relative. So this, so remember, you know, we know what a relative minimum is. Anywhere it has a change of direction from down to up, like these two, would be local minimums. Which, on our sign chart, if you go from negative to positive, because that means you went decrease, then increase, so you don't have to even see the graph. If you go from negative to positive, that's going to be a local minimum, but provided it is an existing point on the graph. So keep in mind that you cannot do that for discontinuities. So a discontinuity cannot be a relative min or a relative max. So this only applies to critical numbers. In fact, that was the definition we saw a while back on one of the other sections, that if you have a relative min or a relative max, then it came from a critical number. But then I also explained, though, that all critical numbers don't necessarily yield min or max. So the theorem said min or max had to come from critical numbers. So if you go negative and positive,
time for lunch.
Critical number, you got a relative min.
When the sun beats down, I lie on the bench.
Maximum means you go from increase to decrease. So if it's always charged with plus or minus, you've got a relative. Now jump back up here just for a second. We'll see this come up again. Let me explain this while it's fresh on my mind. It didn't apply in this particular problem. Let me explain about the dash line there. That's not required from a mathematical standpoint. You know, it could all technically be solid on. But I like to do that, and I put that dash line there. So now that we talk about relative and maximum, if I go back and look at the chart, and I see that I put a dash line there, then I can remember that was the number. But if you don't see that number, you don't worry about it. So in this particular graph, we only have relative extreme of negative 3 and positive 3, not 0. Dash changes. But even though this did not change, if it did change, it's still saying it went from decrease to increase to 0, not a minimum. So actually here we have a relative maximum going increase to decrease to negative 3, and then a relative minimum going decrease to increase like that. problem. Now, it's a little arrow there. We're talking that same chart and everything here, and so we decrease, so there's no discontinuity, so everything's fair game. So the first one goes from decrease to increase. That's going to be relative minimum. The arrows that I drew there aren't required. Just the wording change from increase to decrease. That's going to be decrease to increase is a minimum. And then increase to decrease at pi would be relative maximum. And then we have the last interval would be another decrease to increase, which is the relative minimum. Now this, I just wrote this in kind of like f of x notation instead of x and y or whatever. That's fine. Now on a quiz, on an exam, you may have to get the y value, but that's not mathematically difficult. Just using your calculator if you need to. But keep in mind here, though, if you do have to get the actual points on the graph, that's what these are, but they're just written as f pi over 3. So if, like a multiple choice, you could actually tell by your answer choice. So anyway, so remember, you would plug to get the y value, so you plug those back into the original function. So plug them back into the derivative. That would not help. You already plugged stuff into the derivative. You didn't need it right there. That's it. So plug those back in there. Pick one that's simple enough here. I think like pi, I probably plug pi in there. Here, pi. Cosine of pi is -1. -1 squared is +1. The cosine of pi is -1. So it'll be 1 minus -1, so it'll be 2. The actual point on the graph is pi, comma 2. There we go. There it is right there. The x-axis is scaled by pi over 3, but the y-axis is normal. So there it is. 1, 2. There it is right there. So you plug it back in the original function if you need. If you don't have to, then don't worry about it. Like I mentioned this a minute ago, but Dewey's following it up for us, so that'll give it more authenticity. Dewey says that relative extrema do not occur in discontinuity. And Dewey is 100% correct. Alright, now we're adding, so here we're finding critical numbers, which we have to do anyway. Intervals of increasing and decreasing, and relative extrema. And let's see, so I didn't even mention the continuity here. That's the problem. They're relevant. No chance for a polynomial. Alright, so easy derivative, 4x cubed minus 32. Set that equal to 0, x cubed equals 8. Alright, not plus and minus here. I keep harping on to watch out for that plus and minus, which is true if it's like x squared or x to the 4th or some even exponent. But x cubed, nah. Odd root only has one real answer. There are 2 imaginary solutions buried in there, but we don't care about that. But the cube root of 8 is 2. There's no plus and minus. Well, I got a very simple chart here is only one number, 2, so we're just separating it from negative infinity to 2, and then 2 to infinity. I picked something less than 2, I picked 0. Greater than 2, I picked 4. Put 0 into this derivative. Yeah, I wrote it with actually what it was over here. Negative 32. And then I picked something greater than 2. Could have picked 3. Don't know why I picked 4. I don't know. Doesn't matter, but either one of them's good. So we have 224 positive. That's all we care about, the positive, not the 224. There's the plus. We have decrease. We have increase. We have a relative minimum at 2, comma, f of 2. So that if you actually get what that y value was, plug 2 back in here. Let's see what it is. That's 2 to 4 to 16 minus 64, negative 48, negative 44. Let's have a y axis scale by 10, something like that. Yeah, it's only 4 minutes down. Yeah, so let's scale by 10 and make that graph fit in there. Anyway, we have decrease, increase. There's a whole row of 10 right down there. Look at that. Now this, that fractional exponent where the fraction is less than 1. We'll talk about that on the definition of critical number. When you have that, you're going to get a critical number from the other part of the definition. So you have values that are undefined at the derivative, but they are defined in the original function. But still you get critical numbers equal to 0. You know, by the normal in both ways. Like with this example where that happens both ways. Here you're going to get, you take this derivative 1/3, x minus 3 to 2/3. I'm noting the 1 there to make sure I didn't forget the derivative on the inside. I would have got lucky here, but it's something to depend on luck. Do it correctly. So I drop this down and come up with this. So this fraction can never be 0. 1 can't be 0. So we're not getting any critical numbers that way. However, look what I wrote over here. F prime of 3 would be undefined, but f of 3 is defined. It's all because of that fractional exponent being the exponent being less than 1. That's going to happen every time. Therefore, 3 is a critical number. So it might have been really easy to stop right here and think you had no critical numbers. It's possible. It's unlikely I would ask that on like a test question, but yeah, you have a function of natural critical numbers. An angled line, and they'll look at a critical number like that. But, yeah, so certainly I would not have something. So there we go. So 3 is our point of separation. So negative 3, we go down to test value. 0 and 4, over here. Positive, positive. Plus, plus. So technically, we did that separately. We did not link that together in one area. So it's almost like a 3 is saying there's a temporary halt. So there's increase, increase. Yeah, do phrase that as separate and we'll come back to that. So maybe just say increase involves all real numbers. No, that's not the way we want to say it. You got to do that. It's a critical number. It's a vertical tangent. But it did not produce that's going on our sign chart. And okay. I'm not going to walk through all the steps of the focus rule here, but that's what we're doing. I'll still going to keep that skill to do this at this point and get to the interesting point where we're getting to the critical numbers. So you multiply all that out, combine the terms, be careful though, we'll say following that. And then once we have our derivative simplified, remember we set this equal to 0, we call it 0. I just showed that. it's still part of the derivative. And in fact, you can see there when you're plugging in the test value, consider that. But not for actually getting the critical number. That's the top part. That factors beautifully. You have -3 and -1. So we have two critical numbers and one discontinuity. They all go on the sign chart in left to right order on the x-axis. So here's negative infinity to -3, -3 to -1. Okay, I'm putting that dashed line there, which isn't mandatory, but just to let myself know that, hey, that's a discontinuity. Do not consider it as a relative min or relative max. Then we go -1 to 1, and then 1 to infinity. So we have 4 intervals.
Can you tell me where
So pick test points in each of those intervals. -5, -2, 0, and 3. Here they are in the calculator chart. Notice I did label that as y prime, just so you can see that, that y1 was not the original function. Obviously, my graph up here is the original function. So test value of the derivative, and so you see we've got positive 0.75, -3, -3, positive 0.75. So our sign chart goes plus, minus, minus, plus. So we have increase, decrease, decrease, increase. So we go increase to decrease at that first critical number, -3. Therefore, that will be a relative max.
Time goes by. It's the time of your life.
And then we go decrease to increase the second one.
Easy now.
That'll be a relative min. So we have -3 up, -3, 1 up, 1.
Dreams.
See there's a maximum there at -3. And a minimum is -1.
Digesting England
And if
by
you find the y values, you can plug them back in. You plug those two x's, -3 and +1, back into your original function to get the y if you wanted to. So might not be a bad idea if you just wanted to practice that. Just try that out. See. Then you can look at that graph up there and see how close it is. The next one we've got here, x + 4 over x squared. Definitely have a discontinuity at 0. We do the quotient rule. Now, usually we don't mess with the denominator whenever it's like a binomial or a trinomial. We just leave it squared. But in this case, because it's a single variable x, so I try to do the quotient rule on top. I simplify this, but then I allow, x squared squared to be x to the 4th. Then I go ahead and just simplify that if I can. Usually we don't mess with the denominator. Unless it was a factor it out, common term. That was the binomial term. So anyway, long story short, I'm done with this anyway. The negative x minus 8. Set that equals 0. Get negative x. Critical number. So we have a discontinuity. We have a critical number. The critical number is -8. There's my dash line represents 0. Now this is a good one, so it was actually, the last two, which was the discontinuity, we did not have a change here. So there are my 3 values. I'll put in -10, less than -8, 0, -8, 0, I'll put -2, 0, infinity, I'll put 2, negative, positive, negative. Signs right there, negative, positive, negative, increase, decrease, but because I drew that dash on, don't realize that 0 is not a relative max. Just because it goes increase and decrease, it cannot be a max at a discontinuity. So we only have right over here, that means we have a relative min, -8, that's -8.
There's a fat old lady outside the saloon.
About right there.
Paying out the credit card, she plays for 2. start. And all of their hands are playing the parts. Captain leaves his thumbs right out through the night. Join the dance for the world. Around table talk it down we go. You're the show. Off we go with you. Play the hobby horse. I play the fool. We'll tease the bull ringing round and round, round and round. For the world. With a twist of the world we go. For the world. Till the gold is cold. Dancing out with the moon at night. Nights in the green fields down and shout.
Set that equals 0. I'll bring the sine of x over. Square root of 3. Now there's several ways to go about this. Take this, and I don't have to play this. Put no way to it, but yeah, you could actually substitute this into the sine square from cosine square to 1 equation. Solve that way. Now, if you did different, it's negative. Positive relationship. So with sine of x equals positive square root of 3 times cos of x. That means our values are going to be located in either quadrant 1 and quadrant 3. Meaning they're going to have to be both the same sign. Sine SIN versus SINE. In other words, both positive, both negative. So this is true. But instead of going through, and you could also, but if you have to know what the tangents were, but yeah, if you divided both sides by cosine, that's the same thing as saying tangent equals the square root of 3. That's also correct. But I look at it this way. The cosine of x, cosine is x, sine is y. So all I'm looking for is wherever the sine will be a multiple of the square root of 3 times the cosine. And that's going to occur at these locations, like right here. You see where cosine is 1/2 and sine is square root of 3 over 2. Therefore, sine is the square root of 3 times cosine. And that was the opposite. You go down here, if the square root of 3 was attached to the sine, and look at it that way. So that's all you really have to do, is just look at that multiple square root of 3 being multiplied by cosine, 1, so 1/2. So then you find the one equivalent one 180 degrees across over in quadrant 3. That's the same thing, except where they're both negative. So there's several ways you can go about that to get those two values. But anyway, long story short, it is pi over 3 and it's 4 pi over 3. So we have 0 to pi over 3, pi over 3 to 4 pi over 3, 4 pi over 3 to 2 pi. This time, that other trig problem you saw me use just like number values for radians, which is fine. That was obviously correct. And so here I went kind of a more traditional route that you might want to do. I just picked values that were off the unit circle. Pi over 6 you see is between these two. And then pi would be between those two blue ones. And then I picked 3 pi over 2 right here in between 4 pi over 3 and 2 pi. So whatever works. This certainly might be easier. Then I put them in the calculator. Of course, they turn into decimal as soon as you type them in, even with the pi, they'll convert to decimal. I need to make sure I'm in radian mode. And you see I get positive 1, negative, and positive. So it goes positive, negative, positive, plus, minus, plus, increase, decrease, increase. So we have a relative max. We're going from increase to decrease at pi over 3, f of pi over 3, whatever that is. And then a relative min right here, because it goes decrease to increase, goes down then up, decrease to increase at 4 pi over 3, f of 4 pi over 3. And we can glance at the graph real quick. And this, I don't think I have it labeled here, do I? Let's see. Okay, but the x scale is pi over 3. So that one tick mark on the x-axis is 1 pi over 3. So there's your maximum right there at pi over 3. So you go 1, 2, 3, 4. So that minimum down there is at 4 pi over 3. So we're going to increase, decrease, increase, just like the chart says. And that concludes this video on increasing and decreasing functions.